Welcome to the lesson video on PCA Visualizations. In this video, we're going to talk about PCA, which stands for Principal Component Analysis Visualizations. And so this is the process of using the principal components to better visualize our data. And so the principal components, recall, are the direction of greatest variance away from the mean in the data. And principal components visualizations is projecting the data onto the space spanned by the first few principal components. In other words, we're using these principal components as a new basis for the data. Why would we do this? There's two things you can use this for. For just doing the visualization, this allows us to see relationships even in high-dimensional data. But also, principal components analysis are used as a data preparation method to reduce the dimension, reduce the number of variables, so your models can focus on the important structures in the variance as opposed to the noise and superfluous feature variables. So let's walk through principal components, remind ourselves how they're defined. And so I have a two-dimensional random normal variable, and we're going to walk through what the principal components are. So the first principal component is the vector pointing out of the... So let's walk through what principal components are and remind ourselves how they're defined. So we have here a two-dimensional random normal variable, and the principal components, recall, are the vectors that point away from the mean in the directions of greatest variance. So the first principal component, here's our mean, points away from the mean in the direction of greatest variance. So it's approximately right there. That would be our first PC, or first principal component. The next principal component is the vector that points in the direction of next greatest variance. It's perpendicular to the first principal component. And so we define the principal components iteratively like that. Each new principal component is perpendicular to the previous ones and points in the direction of next greatest variance. So you'll wind up with the same number of PCs as you have feature variables or variables in your data. And the earlier PCs, the first few, are the ones that capture most of the variance. There's a couple of different conventions. Sometimes the length of each PC can be the amount of variance in the direction of that PC, and that's how we've drawn them here. PC1 is long because it points in the direction with the greatest variance, and PC2 is going to be smaller. Sometimes people will use the principal components, so use unit vectors as the PC, and they'll have the associated eigenvalue to be the amount of variance. And those are the eigenvalues of the covariance matrix. And remember, the principal components can be computed as the eigenvectors of the covariance matrix for your data, and then the amount of variance in each direction are the eigenvalues that are associated with those. And we can think about the principal components as giving us the direction and the span of the ellipses if we're modeling our data as a multivariate random normal variable. Okay, so let's walk through an example of projecting the data onto two principal components. So this is three-dimensional data. And in this three-dimensional data, we have three classes, and they lie approximately on a sphere. And it's a little hard to see in this picture, but the mean of the data is about in the center of the sphere. The first principal component points approximately out towards us, and the second principal component points in that direction towards the blue class. Now, here's the data without the sphere in this first plot here, and this plane that we have in here is the plane spanned by the first two principal components. So the first one points roughly that direction, the second one points that direction, and then these two vectors define a plane. And if you take each point and project it into the closest point in that plane, that gives us this picture that we have right here. This is the projection onto the plane spanned by the first two PCs. And so the first PC is here, and the second PC is there, right? And there are the variables we're using for our axes. So the coordinate for each point in this plot on this principal component projection is the amount that point is away from the mean in the direction of that principal component. So this gives us a way to take this three-dimensional data where maybe it's hard to tell if things are separable, but once we get it into this two-dimensional data over on the right-hand side, we can visually see, oh, there seems to be some pretty reasonable separation, maybe not perfect with linear decision boundaries, but pretty close. These classes are pretty separable, something that would be harder to see in the original space. whereas this is going from 3 dimensions down to 2. If we went from 100 dimensions down to 2, you're taking something where it's really hard to see through scatter plots what's going on 100 dimensions and making it possible to visualize things in 2 dimensions. Another really nice property of principal components, projecting into the plane defined by the first k PCs gives the best k-dimensional approximation to the data. So what does that mean? In this picture, we took the data, then we have this plane that's spanned by the principal components, and we project the data into the plane. So if instead of projecting in this plane, if you rotated that plane a little bit, project it into a different plane, the mean squared error computed from these black lines from each plane to how far it has to go to get projected into the plane would be larger for any plane other than the one spanned by the first k PCs. Okay, so let's walk through some PCA visualization. So here we have some data from the US arrests data set. We have 3 feature variables here called assault, murder, and rape, and there's a number of arrests for each of these crimes per 100,000 people. So if this variable is, say the variable assault is 200, that means that 200 people are arrested for assaults for every 100,000 people in the state. Then we have this feature variable called urban pop, which is the percent of residents visiting in an urban population. And there's a warning here, be careful of units in PCA. We'll talk about this a little more in a moment. But if we take these variables as they're given, urban pop is in a 0 to 1 scale, and the assault, murder, and rape are on a very different scale. And so things will look funny. And we'll take a look at that. But what you often do is you scale each variable to have a mean of 0 and a standard deviation of 1 before applying the PCA visualization. And so what we observe here in this PCA visualization on the right, so this is principal component 1, that's principal component 2, or we can just reference the labels on the axes. PC1 is pointing in direction of greater crime in general, and a little bit in terms of urban population. Principal component 2, if we look at the cities or the states that are captured by principal component 2, looking in the vertical direction on this plot, New Jersey, Hawaii, Rhode Island, California, those are very urbanized states. The ones that are in the opposite direction from PCA2, South Carolina, North Carolina, Mississippi, those are less urban population. So PC2 corresponds to urban population. We can see that because urban population is put in here, shown with this orange vector. It shows you the direction of urban population. There's some nice organizational data that we observe here that these assaults group roughly in the direction of the first PC, and urban population is more in the direction of the second PC. So here's another example. We have the zip code data. And so this zip code data is a standard data set that people look at. Each observation is a digital image of a handwritten number. In this case, we're just looking at the number 3. So there's shown here 130 different 3s. It's a digital scan, 16 rows and 16 columns from a number 3 that was written by a person. When we apply PCA to this data set, right, the data set, each data point is in 256 dimensions, right, and that's the 256 is the number of pixels in the image of the data of the number. We can plot the data in the first 2 principal components, right? First one is a horizontal axis, second one is a vertical axis, standard. So this data point here corresponds to this 3. This data point here corresponds to this 3, and the grid of circled data points in the scatter plot corresponds to this grid of 3s over here. So if you look at the first principal component, which is the variation in the 3s we see in the horizontal direction, that has a lot to do with the width of the 3. So if you see this 3 is wide and this 3 is narrow. So the first PC is capturing the width of the 3. If you look in the vertical direction, the variance in the vertical direction has to do with the thickness of the ink or the pencil or whatever it is it's writing, so the thickness of the letter. So second principal component is capturing the thickness. So this tells us in these handwritten 3s, the main variation that occurs because the width of the 3 varies and then the thickness of the lines in the 3 varies. And we can look at further PCs and see what type of variation there is among the number 3 when people write 3s after that. So this, going back to our urban population US arrests data, the left-hand side is the scatter plot we're looking at, where the data are scaled before, and the right-hand side is when they're unscaled. And so this is a reminder that we may want to scale the data before applying the principal components. Another thing that comes into play with the principal components analysis is you can look at the amount of information in the however many PCs that you're using. And this is something that comes in that's important, both when we're using dimension reduction to improve modeling, but also we're looking at scatter plots. We want to know how many principal components do we want to use, and then look at scatter plots involving those PCs. So we saw a few examples where we just took the first 2 PCs, but we could take the first 5 and look at all scatter plots that involve the first 5. Right? That's a lot easier to do when our native dimension of our data is 256. So the way we tell if our first K principal components, maybe K is 5, maybe I'm looking at the first 5, if that captures a lot of the variance, is we look at the amount of information captured by the kth PC, and that's the amount of variance in the direction of that PC divided by the total variance. And so that's the percent of information, or the percent of variance captured by that PC. Then we look at the first K PCs collectively. It's the sum of the amount of information, or the proportion of information captured by each individual principal component. So here on this axis, let's look at the first plot, the left-hand side plot. We have principal component on the horizontal axis. So this is the number of principal components, or the number for the principal component we're looking at. And the vertical axis is the proportion of variance explained. So the first PC, number 1, explains 60%, 0.6 of the variance. Second PC, number 2, captures 35% of the variance. The third PC captures maybe 10% of the variance, not much. And so what we often look at is the cumulative proportion of the variance explained, or the amount of variant information contained in the first K principal components. So one principal component by itself captures 60% of the information. 2 principal components will capture maybe 95% of the information. So that would tell us, for this example, this is the USA arrests. When we're looking at it, we see 95% of the information, or 90% of the information. And that scatter plot shows us most of the variance that exists in that data. There's some other principal components, 3 and 4, and they don't capture much of the data. And so another way to think about this is that it tells us that there's a lot of spread in one direction, a little spread in the next direction, and then these extra directions have very little spread. So here's another use of principal components. This is an example where we have 200, it's a visualization of ethnic groups based on RNA. And so we have 2,654 observations from 16 ethnic groups. The features here are about 186,000 single nucleotide polymorphisms. So these are genetic variations that can be detected. And so we have 186,000 feature variables. So it's a large number of feature variables, really high dimension. We're in 186 dimensional space. Hard to imagine, hard to visualize, but using principal components, we can project that down onto the first 2 PCs, and we can look at the eigenvalues for the first 2 PCs, and those are fairly high compared to the eigenvalues as you go down the list. So a lot of the information is captured in the first 2 principal components. And the plot you see on the right-hand side shows this data projected onto those first 2 principal components. And we could see here that you can see the geographical connection, South Africa, West Africa, through East Africa, through North Africa, and then things that are close to North Africa, and then East Asia going into those Central Europe and Middle Eastern directions. So there's variation that occurs in these SNPs that seems to correspond to distribution of humans across these continents. So review what we talked about with PCA visualizations. They involve projecting the data onto the space spanned by some smaller number of PCs. In other words, using the PCs as basis vectors and viewing scatter plots of the data for these. Why would we do this? This allows us to see relationships even in high-dimensional data. We can estimate the amount of information in the first k principal components, and this tells us how much of the total variation that we're looking at when we look at these scatter plots. This allows us to get some idea of the shape of the data or relationships between groups within the data, even when the original data is in a very high dimension where we couldn't normally see it. Well, thank you very much for watching.